All right, class, welcome to Lab 12 for week 12. We're going to start looking at exponential functions and then logarithm functions, and I'm going to show you how they are connected to each other. So the first thing we're going to talk about is we're going to look at graphing exponential functions. So really quickly, I want to go over kind of what an exponential function should look like and all the different parts and pieces. So over here to the side, we're going to do, first of all, a function for an exponential is going to be y equals a times b to the power of x, okay? A is our starting value. That is where we're going to start our graph, or it's going, actually, sorry, it's not just our starting value, it's actually our y-intercept. I'm going to write that differently. All right, so that's our y-intercept. That's a better way to put it. B is obviously our base. Okay, but there's a thing. So if b is greater than or equal to 1, he represents growth. If b is less than or equal to, sorry, is less than 1, not equal to, is less than 1, then that represents decay. And of course, x there, well, he's just our exponent. All right, so let's take a look at two different graphs. The very first one, again, we're going to look at it, and we have 4 to the power of x. Now, if I were really looking at this, I know that this is actually y equals an understood 1 times 4 to the power of x. That's actually something that you do need to get used to making a note of. Even though there's not an a there, there could be. It could be 2 times 4 to the power of x, or 6 times 4 to the power of x. Whatever it is, he is your y-intercept, and when there's nothing there, he is an understood 1. So it wants us to graph it, so we're actually going to create our table, right? I have an x, I have y, and I'm going to choose some values. Here's the thing. I always choose 0. I'm always going to do a -1, a 1, and I'm probably going to do a -2 and a +2. I tend to do 5 points whenever I do this, but remember, you're always going to have your 0, and you're going to choose a couple before it and a couple after it. All right, so what we're going to do is we're going to plug it in. We know that if I plugged in, what's that, 4 to the power of -2, that is actually 1 over 16. Yes? No? Yeah, 16. 1/16. So we know we're going to have a point at -2 and 1/16. So -2 and 1/16 somewhere down here. Not perfect, but down there. All right, and then we have 4 to the power of -1. Well, that's just 1 over 4. So I have a point at -1 and 1/4. So -1 and 1/4. And we're going to say here. Doesn't have to be perfect. Our y-intercept, well, our y-intercept we should technically already know, but 4 raised to the power of 0, well, anything raised to the power of 0 is 1. So I know my y-intercept is 1, or I should have an understanding that if there's nothing there, the y-intercept is 1. 4 raised to the power of 1 is just 4, so I have a point at 1/4. And then 4 raised to the power of 2, 4 squared is 16. So I have 1 and a point at 16. Obviously that doesn't, or sorry, that's a 2. So I have 1 and 4, and of course 2 to the power of 16, well, I can't do that. That's going to be way off my graph, so I'm not worried about him. Now I'm going to draw my line. Remember, he gets really close to the x-axis, but he's not actually going to cross it. So this will have a horizontal asymptote of 0 because it gets really close, but it does not actually cross. All right, for b, I have 1/4 raised to the power of x. Well, it's a fraction. It's less than 1, so I know that this is going to be a decay problem. So I know he's going to go and look like that. All right, so now I'm going to take and I'm going to plot some points again. I'm going to go my x, my y, I'm going to choose 0. I'll choose -1, 1, and I'll choose 2 and a -2. All right, so now I have to plug them in. Remember, this is an understood 1 in the front, so I know I'm going to have a 1 on my graph as my y-intercept. So that'll be out 0, 1. Now, whenever I raise a fraction like this to a negative exponent, remember it's going to actually flip it, and then you'll square it so that this will just be a positive 16. So I'll have a point at -2, 16. We have 1/4, again, raised to the power of -1 means that he's just going to become a 4. And I have a point at -1, 4, which I will do -1, 4. And hopefully you're seeing the same pattern. We have 1/4 raised to the power of 1 is just 1/4. So 1 and 1/4. And then, of course, 1/4 squared is going to be 1/16. Remember, he's really close, but not quite there. Then we just take and connect our dots. So we're going to start up, and we're going down. Remember, I'm not actually going to cross the x-axis. I'm going to get really close. So again, this has another horizontal asymptote of 0. We will use that when we are looking at our range for these problems. All right, let's move on. It says, do the functions from number 1 represent exponential decay or exponential growth? Well, A, obviously, right? The B was greater than 1 or greater than or equal to 1, so it was growth. For B, it was a fraction, right? So B was less than 1, so we know that it represents decay or exponential decay. It says, what is the domain and range of each function from number 1? Again, what's really nice about functions for domain and range, or domain and range for these types of functions, your horizontal asymptote is going to affect your range and only your range. So we have, for A, if we go back and look at it, right, our domain, well, from left to right, it's going from -infinity to +infinity. So our domain is -infinity to +infinity. Now our range, right, that's from bottom to the top. So from the bottom to the top, it's affected by the horizontal asymptote, which we said was at 0. So I know that it will not cross the 0. So my range starts at 0. And it goes up to +infinity. B is exactly the same. The domain is from -infinity to +infinity. But the range is affected by that horizontal asymptote. So it goes from 0 to infinity for my range. Okay. Now we're going to talk logarithmic expressions. All right, so we have log base A of x. I have seen it log base A. I prefer to use log B of x. Personal preference on that one, but I just like to use log B, log base B. It'll make sense in a little bit whenever I go over it. When we see log 3 of 9 equal to 2, we say log base 3 of 9 is 2. And we then think 3 to what exponent? As I spell what wrong? To what exponent or power is 9. All right, let's look at this. This is how we go to rewrite it. We look at that and we go log 3 of 9. Okay, so we have a base of 3. We don't know what the exponent is, but we know that it is equal to 9. So I need to know 3 raised to what power will give me 9? Well, if I know my exponentials, I know that this is 2. That 3 squared is equal to 9. All right, again, we have log 2 of 8. So I know base 2 of what exponent equals 8. Again, if I know my exponentials, I know that that is raised to the power of 3. So 2 cubed is equal to 8. Again, we have 3 raised to what power is equal to 27. 3 squared is 9, and 3 cubed is 27. So I know that this is a cube that we need there. Now, we're going to go over some additional properties. While we're doing this, I'm going to make notes of some rules that we use to solve these problems. Now, if we look at the very first one, we have ln, or natural log. So ln means natural log. You will see me use a cursive L so that it's not mistaken for a 1. So ln is equal to natural log. And natural log is undone by a 1/2, or it is canceled out. Sorry. Natural log is canceled out by e. Okay, so really what happens is I go, okay, ln is canceled out by e, so my answer is 1/2. So I'm going to make a little note over here to the side. All right, and this is for answer A, or problem A. I know that natural log, or ln, is canceled out by e. Okay, for part B, I have log 10. Well, how do I solve this one? Anytime you see a log and there is no base to the bottom, we actually can say that that is now an understood base of 10. So if I have a log base 10 of 10, well, I say, okay, 10 raised to what power is equal to 10? Well, nothing changed, so it's a base of 1. Another way that you can look at this, well, actually, no, we'll do it here in a second. All right, so I'm going to make another little note here to the side. If you are given, so if you're given log with no base, okay, it is an understood log base 10. All right, if you're given just a log, it is an understood log base 10. Now, C. This is where it gets fun, and we have to use, we have to change some things or manipulate some things to solve the problem. But it's really easy. If you know your exponentials, if you know your power properties, then you'll be fine. So in order to solve log base 5 of 25, right, we say log base 5 of, 5 raised to what power is equal to 25? Well, 5 squared is equal to 25. Another way that I like to do this is I change the problem, right? I have a log base 5, and in order for me to solve this problem, I'm going to change that 25 to a base of 5. So I know it's 5 squared. So then those two things cancel each other out, and I'm left with the 2 as my answer. So those are two methods to use, right? Again, we have 5 raised to what power is equal to 5? Well, that's a 1. Another way to look at it is if we had log base 5 of 5 to the power of 1. Again, those two things cancel out, and I have an answer of 1. So log base 2 of 2, again, whenever they are exactly the same, they end up becoming just an answer of 1. All right, now this is where it gets a little more complicated. We have 2 raised to what power is equal to 1/2. Well, what makes a number become a fraction? Well, of course, a negative exponent. So we have a negative 1 because that 2 did not change. Okay. Log 2 raised to what power gives me an answer of 16? Well, 2 raised to what power gives me 16? If I know my exponents, I know that that is a 4. Remember, if you don't know it, start playing around in a calculator. Do 2 raised to the power of 3, 2 raised to the power of 4, 2 raised to the power of 5, whatever you need to do. But another way of looking at this is we use a change of base. So we have a log base of 2, and I say 2 raised to the power of 4 is equal to 16, so that those two cancel out, and I get a 4. All right, again, I have 4 raised to what power is equal to 16? Well, I just did that. I know that 4 squared is 16. Again, another way to look at it, we use a change of base property, where we do log base 4, and I change that 16 to a 4 squared, so that I get an answer of 2. This one's fun. 2 raised to what power is equal to 1? Well, this is where you need to know a little bit of a power property. And any number raised to the power of 0, 1. So I can make this any number that I need it to be, but regardless, 2 raised to what power gives it an answer of 1? Well, that's of course 0. All right, well, then we have 2 raised to what power is equal to 1/4? Well, it has to be negative in order for it to become a fraction. And of course, to get a 4, it needs to be a square. So a -2 squared. Again, 3 raised to what power is equal to 1/9? I know that it has to be negative to make it a fraction. And to make that a 9, it has to be a square. All right, log of 1. Again, how do I get an answer of 1? Well, it needs to be, well, actually, I don't, I'm going to show you my way. Remember, that's a log understood based 10 of 1. So I say 10 raised to what power is equal to 1? Well, remember my property. Any number raised to the power of 0 is 1. So I know that that exponent has to be a 0.